Hello everyone, this is the presentation conducted by Zhang Sungli for the ICCV 2023. The title of our paper is SlaBins Fisheye Depth Estimation, using slanted bins on road environments. First, let's talk about our motivation. With the advent of autonomous driving, the importance of 3D perception keeps growing for safety. Here, many previous works and datasets For the side view 3D perception, there are many attempts to use fisheye cameras in side view. As you can see in the slide, fisheye cameras have a larger field of view than perspective cameras, which can handle large area information with only a single camera. Regarding these advantages, it is hard to use a pre-trained model in the fisheye image domain because of generalization. Then, what makes it difficult to learn 3D perceptions in fisheye cameras? Compared to normal cameras, in the fisheye image domain, there are lots of camera distortions that bother the network to learn image features. Furthermore, if the fisheye cameras are slanted, objects go in the edges of the image and become smaller because of its distortion. These special properties make our problem hard. So, our goal is to build a robust depth estimation network that can predict depths regardless of the camera's slanted angle. Before going to our method, we will describe various multi-layer image representations. First of all, let's see the most common method called multi-plane image. Multi-plane images are used in perspective image depth estimation because they generate depth plane in front parallel. However, in the wide FOV cameras, we use different multi-layer image representations called multi-sphere images and multi-cylinder images. There are some advantages and disadvantages. We decided to use multi-cylinder image representation because most objects stand on the ground in the real world. In our paper, we use slanted multi-cylinder image representation especially. This is our slanted multi-cylinder image representation notation. As shown on the left side, the gray cylinder indicates cylinder in camera coordinate, and yellow cylinder layers mean slanted cylinder layers, which we used in our paper. Alpha, theta, and phi denote the camera's slanted angle, elevation, and azimuth angles, respectively. By using these parameters, we can transform points in the original cylinder to the slanted cylinder from equations 1 and 2 below. Here, we will give you an overview of our proposed network architecture. Our model consists of 3 parts: feature extraction module, slanted angle prediction module, and SlaBins module. For the feature extraction network, we used efficient net-in encoder and simple decoder. Here, we extract features with a smaller resolution for efficiency. The slanted angle prediction module takes the output of the feature extraction network as input. It predicts the camera's slanted angle into steps. For more accurate prediction, we adopt classification and regression methods. For the last, our SlaBins module predicts the final depth map. Through the VIT, the network predicts per pixel probability and bin centers. By combining this information, we can get slanted MCI depth. However, our target domain is Euclidean distance. We convert this slanted MCI depth to the distance using transform function f with slanted angle alpha. Let's see the results. In the synthetic woodscape dataset, our method can predict more distinguishable depth maps than other methods, especially in object ground boundaries. Object regions are zoomed with blue boxes for better visualization. In the KITTI-360 dataset, our method also shows better results in object region. These are the qualitative comparison results on both SynWoodScape and KITTI-360 dataset. In the SynWoodScape, our method outperforms previous methods in a huge gap. However, the performance in KITTI-360 dataset shows slightly better than SlaBins, which uses multi-spherical image representation. To validate our proposed slanted MCI representation, we performed ablation study between original MCI and slanted MCI. As shown in the slide, you can see that depth from slanted MCI is more similar to the ground truth than original MCI, in terms of MCI depth. In conclusion, our work proposes a new fisheye depth estimation framework called SlaBins. We newly introduce a slanted MCI representation that makes depth into slanted MCI depth. By using slanted MCI representation, our network can estimate depth regardless of camera's viewing direction. This is because our framework estimates slanted angle and use it for slanted-aware depth regression. This is the last slide. Thank you for listening our presentation.